Hello guys, so now our next topic is lateral displacement. It is again very interesting and very easy. We are covering this in very short lectures so that things are organized and you understand it very well. So this is lateral displacement. What is lateral displacement? We don't know. We are basically going to consider a glass slab from which a ray of light has to pass. Okay, so we will use the concepts of refraction that we have learnt till now. So let's see. First of all, let us see this. An incident light is falling on the one face of the glass slab. Wherever you are putting incident light, and here there is an interface between air and glass, please draw a normal. This is a minimum requirement for optics. Wherever there is an interface and as soon as the point of incidence is reached, draw a normal. So I have drawn a normal. If you see, a normal has been drawn and the angle made by incident ray with normal is called incident angle or angle of incidence, that is I. Okay. Next, it is traveling from air to glass. That means from optically rarer medium, it is traveling to optically denser medium. Velocity will decrease. Light's velocity will decrease in an optically denser medium like glass. So as the velocity of the light will decrease, that means it is going to bend towards the normal. See, it has bent towards the normal. Okay, and this is angle of refraction. Okay, now it is hitting another interface, that is from glass face, the second face of glass block to again to air. Now again when I am reaching one interface, I will draw another normal from this point of incidence which I have marked as O dash. Next is, there will be one angle for this refraction. For this refraction from glass to air, there will be angle of incidence, right? I have marked it as R2. Now let us check this. If you see this line OP and if you see this line O dash P dash, both are basically normal to AB and CD. So this must be parallel, right? This must be parallel. So I can write OP parallel to O dash P dash. In case these two lines are parallel, then what happens is the angles PO dash becomes equal to the angle P dash OO. P dash O dash O, sorry. Because these two are alternate angles and OO dash is transversal. Because OP parallel, because there are three reasons: OP parallel, O dash P dash. Number two, first of all you write alternate angles are equal. Alternate angles are equal because OP parallel O dash P dash and OO dash is transversal. Okay, clear? So as PO dash okay, is equal to P dash O, that means R1 is equal to R2. Clear? This has to be. And also we will get another relation over here. If you see, this is angle I and this is angle R1. So at this moment, if I want to calculate what is the refractive index of glass, that is A from air to glass, that means A mu G will be sin I by sin R1, Snell's law. Always write in bracket from which you are getting all these things. This is very important. Okay. So A mu G is equal to sin I by sin R1. And if I take the next one right now, I have marked this angle. This will going to refract away from the normal because velocity of the light in glass is less, and again it is going to air. That is, the velocity will be higher, and hence it will go away from the normal. And this angle we call as E, that is called angle of emergence. Okay, angle of emergence. Now let's take this refraction, that is glass to air. What is the angle of incidence over here is R2 by sine. Angle of refraction over here is E. Okay, done. Now by principle of reversibility, just give me a second. Okay, sorry. Just by principle of reversibility of light, we know that A mu G is equal to 1 by G mu A. We know this, right? So what is A mu G? A mu G is sin I by sin R1 is equal to 1 by G mu A, that is, this is going to get reciprocal, that is sin I E by sin R2. Now R1 is equal to R2, that means I can write sin I by sin R1 is equal to sin E by sin R1 again, because R2 is equal to R1. This one and this one will cancel out and we'll get sin I is equal to sin E, and hence we can get I is equal to E. That is, angle of incidence and angle of emergence is proved, and I proved it by mathematics. I have not just said you on this thing. This is proved by mathematics. Okay. So now these two angles are equal. What does this mean basically? Let's see. If I would have extended this incident ray like this, okay, and again just this an imaginary line, then if you see, this is normal again, okay. So if you see this one, this line and this line is parallel, right? This line and this line is parallel, and let's mark this as O double dash. So O double dash is a transversal, okay. And if you see this one and this one shall be corresponding angles, right? Shall be corresponding, and it should be I, correct? Now if you see this one, this should be again I, vertically opposite angle, correct? It should be I, vertically opposite angle. And if see both these lines, now let's take O dash, let's take it Q dash, and O double dash Q double dash. So O dash Q dash and O double dash Q double dash, both these lines makes an angle I and E with the normals to this DC. Now this is parallel, okay, and with this line, the same line basically, because angle is same, because this is I, this is E, that is I is equal to E. Already I have said that I will be equal to E, and these two are equal. So if these two are equal, what does this mean? There is one parallel line like this, there is one, these two are parallel lines, okay, parallel lines. So these two, P dash, O dash, and let's take this P double dash, O double dash. These two are parallel lines, P dash, O dash, P dash double dash, O double dash, okay, parallel lines. Now if I make an angle theta with this, okay, and if I make the same angle theta with this, then isn't this two line is also parallel? Has to be, right? It has to be. So these two lines, that is O dash Q dash and O double dash Q double dash, is also parallel. Okay, that's what I wanted to say. The incident ray and the emergent ray are parallel to each other. Important point, after lateral displacement, passage of complete light through the glass slab, at the end of the day, the incident ray and the emergent ray shall be parallel to each other. But it will have some distance between the two, right? This is the distance between the two. This distance remains constant, right? Because they are parallel. So this distance is called lateral displacement. Okay, this distance is called lateral displacement. That is perpendicular distance between incidence ray and emergent ray. Write it this down. Perpendicular distance between incident ray and emergent ray after the light passes through the glass slab is called lateral displacement. After the light passes through the glass slab is called lateral displacement. Now, on which factors will this depend? So we have proved everything. It's not that I have said and you have remembered, right? These mathematical proofs are very important in case of physics. Physics without mathematics is nothing. So what are the factors on which this will depend? Let's see. I'll rub this. Too much complicated diagram. It has become so many markings, angles, geometry, etc., etc. Too many things. Maybe they won't write the answers in the same way as you will do. So that will make the difference. Now let's get to another part. Now our next part is lateral displacement and what are the factors? Number one is thickness of glass block. Let's take this thickness first. Normal. So here the incident ray is coming, bending towards normal, again going out. So you draw this like this. This is the lateral displacement. Okay. Now if I increase the thickness, let us take this one. If you see, now the lateral displacement has increased, right? So as thickness increases, lateral displacement will increase, because as the thickness increases, it goes more and more in the bend direction and it goes straight. The distance will increase more and more, you increase the thickness of glass. Number two is angle of incidence. So we'll take the same diagram. If I have increased the angle of incidence like this, okay, let's see what happens. Obviously my refracted ray will also be a little bit less bending, because the angle of incidence and angle of refraction is more or less in the same way, because the refractive index is constant. After this will go, it will go parallel to this. So first I will draw this one. See, in this case, if you see, the lateral displacement will again increase. Okay, so even if you increase the angle of incidence, if angle of incidence increases, lateral displacement also increases. Okay, if angle of incidence increases, then lateral displacement also increases. Okay, I will suggest you draw by scale, take some angle as I have done, and see, measure it and see what happens. That will be better. Third point is refractive index, that is mu. See, as mu increases, what will happen? I will take the same diagram, hope you have drawn it. So let's just have two glass slab with different refractive index. This one, first this falls like this and it goes like this. Suppose this is having a refractive index of say 1.5. Now let us take another glass of same dimension, refractive index of 1.2. That means this is not going to bend that much as this has done. So this will be a little bit like this. So if I tend to, so this will be LD. If I do this one, this will be LD. So what can I see over here? As refractive index increases, the lateral displacement is getting increased. Okay? Because as refractive index increases, the bending towards normal is also more, and hence the lateral displacement will increase. Next is color of light. See, color of light directly affects the refractive index. So suppose if the wavelength, color of light is a function of wavelength, we know. So if the wavelength increases, then what happens? Refractive index, we have already studied this, decreases. If the wavelength increases, refractive index decreases. If refractive index decreases, then lateral displacement also decreases. So obviously lateral displacement will be least in case of highest wavelength, that is red light, and it will be least for red light and highest for which light? Violet light, okay, in visible range. So that is it all for lateral displacement part. Next topic, another small topic will come up, multiple images in a thick plane glass plate or a thick mirror. Okay, thank you.